So today we are going to discuss about the derivation of the Feynman path integral in position space or coordinate space, starting from the path integral in phase space. And in our earlier lecture, we already had derived the path integral in phase space, and it is given like this. That is the equation 1. Okay. And here in this equation 1, we have here the Hamiltonian for a particular system. So here this Hamiltonian is actually the most generalized version for a system. So now this Hamiltonian can have the mixed term, that is, it may contain the momentum into some position or momentum square into some position term. Okay, because it is the most general form of the Hamiltonian. Okay, so let me just write it first. So we have the most general Hamiltonian H, and it is a function of position and momentum, and it is equal to E square by 2m. It is nothing but the kinetic energy term plus some potential term plus some mixed term. Okay, so these are the possible term in for a particular Hamiltonian, and these terms are called as the mixed term. And if we have this kind of mixed term in our Hamiltonian, then the expression for path integral is this equation 1. Okay, and now suppose if we constant ourselves, or we can say that this Hamiltonian is the, or we can say the momentum dependence of this Hamiltonian is confined to a quadratic term, that is this kinetic energy, then this integral over this momentum can be carried out explicitly. Okay, so this is our claim, and then after doing the integration, we'll see that actually this path integral in phase space automatically it will reduce to the path integral in position space. Okay, so this is the motivations for this class which we are going to do. So before we start deriving, let me just first write some of the equations that we already had derived in our last lecture. Okay, so in deriving this equation 1, we had started with equation which we already had derived in our first lecture. So we have the equation of the form x of f u of t xi is equal to integral multiplication starting from k equal to 1 to n minus 1 dxk, again multiplication starting from k equal to 0 to n minus 1 xk plus 1 minus I delta t divided by h cross into Hamiltonian operator and then xk. Okay, so let me just give it equation number 2, and from this equation actually we had to derive this equation 1. So now this is our the most fundamental equation. And here this part can also be written as like this. This also we already had derived in our last lecture. So this part is nothing but limit delta t tends to 0 integral dpk divided by 2 pi h cross exponential bracket I by h cross delta t bracket p of k x k plus 1 minus xk divided by delta t minus h p of k xk bar bracket close. Okay. Now you can see carefully that when this delta t tends to 0, then this expression is nothing but our x dot. Okay, so I can write this expression like this also. If we put the in place of Hamiltonian, if we put the term the kinetic energy plus potential energy term, then we will have following. So limit delta t tends to 0 integration dpk divided by 2 pi h cross exponential bracket I by h cross delta t bracket pk xk dot minus, in place of this Hamiltonian I can write pk square divided by 2m minus potential term. Okay, so this is our potential term, and let me just give it equation 3. Fine. Now to solve this integral, let me just rearrange this term, and then it will be very much easy to solve this integral. Okay, so now I can write these two terms like this, that is minus 1 by 2m bracket pk minus mxk dot whole square minus mx square xk dot square bracket 2. And now I can also choose that I can also define that let pk prime be the new variable which is equal to pk minus mxk dot. Then now I can easily write out this equation 3 in terms of this pk prime variable. Okay, and it is given as follows. So I can write down equation 3 as follows. So limit delta t tends to 0 integration starting from minus infinity to plus infinity dpk prime divided by 2 pi h cross exponential bracket I by h cross delta t bracket minus 1 by 2m pk prime square plus m by 2 xk dot square minus v xk bar. Okay, fine. Now, as you can see that these two terms, this term and this term, are not function of this p prime. So I can take it out from this integral. So let's do it. So we will have the limit delta t tends to 0 exponential I by h cross delta t bracket m by 2 xk dot square minus v of xk bar bracket closed into integration from minus infinity to plus infinity d pk prime divided by 2 pi h cross exponential bracket minus I delta t divided by h cross pk prime square divided by 2m bracket close. Now it is very much easy to solve this integral because this integral looks like a Gaussian integral, and let me just name this integral as I. Okay, so as I said, this integral is now easy to solve because it looks like a Gaussian integral, and we know that for Gaussian integral, it looks, if we have the integral of this form, that is integral from minus infinity to plus infinity dx exponential minus z x square, then the solution to this integral is pi divided by z. Okay, so this is the solutions that we should get. So now if we compare this integral with this integral I, then it is very much easy to show that this z is nothing but, in this case, I delta t divided by 2 h plus m. Okay, then this integral I now becomes like this. So we have here 1 by 2 pi h cross, and we have here this term pi root over of pi by z. So we just have to put here. So if we do that, we will get 2 pi h cross m divided by I delta t root over, and on simplification I will get m divided by I delta t 2 pi h cross root over. Okay, fine. Now I can put this value of this integral I in these equations, then we will get the further solution. So let's do it. So if we put this solution in this equation, then we will have following. So finally, we will get at limit delta t tends to 0, m divided by I delta t 2 pi h cross root over exponential bracket I delta t divided by h cross bracket m by 2 xk dot square minus e xk bar. That's perfectly fine. And let me just give equation number 4 to this equation. Okay, so now we found that this value is nothing but this equation, right? So this value, this equation number 4, we put in this expression, then I can write equation 2 as follows. So now equation 2 becomes x of f u of t x of I is equal to integration multiplication from k equal to 1 to n minus 1 dxk, again multiplication starting from k equal to 0 to n minus 1 bracket limit delta t tends to 0 m divided by I delta t 2 pi h cross root over exponential bracket I delta t divided by h cross bracket m by 2 xk dot square minus v xk bar bracket close. Okay, fine. Now I can take out, because this is just a constant term, so I can take out from this integral. But here notice that this whole term is multiplied with this multiplicative symbol. So there are n numbers of time these terms are multiplied. So when I take out this constant term from this integral or from this multiplicative symbol, then this term will reach to the power n. Okay, so I can write it like this: limit delta t tends to 0, m divided by I delta t 2 pi h cross power n by 2. Again, integral, this integral, and it is equal to multiplication starting from k equal to 1 to n minus 1 dxk. Now we have this term also, but for this term also we have this multiplication symbol. So if we take this multiplication symbols inside this exponential, then it becomes the summation that we all know. So I can write the exponential I delta t divided by h cross summation k equal to 0 to n minus 1 bracket m by 2 xk dot square minus v xk bracket close. Okay, fine. Now I can just name, or I can just define that this term, let this term is nothing but the n, the normalization constant that we will see later. And I can say that, well, this term, for this term, let me denote it as integral d of x. Okay, then this expression becomes like this, that is n integral d of x exponential bracket I by h cross integral 0 to t d tau m by 2 x dot square minus v of x. Okay, so now let me just first of all explain that why I wrote this term like this. Okay, so when this delta t tends to 0, then this integral, this summation becomes the integral. Okay, so for this I just denote this delta t, or I can write that when delta t tends to 0, then I can express this expression like this. That is, when delta t tends to 0, then delta t summation starting from k equal to 0 to n minus 1 m by 2 xk dot square minus vx k bar tends to 0 to t, because this summation becomes this integral, and dt becomes d tau, just a notation, m divided by 2 x dot square minus v of x. Okay, so this is what we have written here. Fine. And now you notice that this is nothing but our Lagrangian L. Okay, and it is a function of x dot and x and probably time also. So now I can write this expression is nothing but our action functional, or we can say that this is nothing but our classical action functional. So I can write this equation like this, or this equations becomes like this. So it's our final equations, or we can say that the path integral in coordinate space is this. So equal to the normalization constant integral v of x exponential bracket I by h cross s, and here this s is a function of x dot x bracket. So now you can see that this is nothing but the expression for path integral in coordinate space. that we already had derived in our first lectures. So from this discussion, we saw that whenever we have the Hamiltonian, which is of the form p square by 2m plus v, and this Hamiltonian is or when we constant ourselves that the Hamiltonian has only quadratic momentum torque, then the momentum integral can be carried out explicitly, and then the final expression for our path integral becomes like this. Okay, so this is the most important rule, because if we have a system in which the Hamiltonian has some mixed term, then in that case we cannot use this equation. Okay, so in that case we have to use our equation number 1, that is this equation. In that case we have to use.